Alright, I'm going to continue 2.3. So 2.3 was dealing with functions. Last time we identified a few different terms. We talked about what a set was. We talked about what a relation is, a collection of ordered pairs. And we talked about the domain. We talked about the range. And then we talked about how to identify if a relation is a function. And from there, we try to verify it in different ways. First, we just looked at the relation to see if it was a function, and then we created a mapping of it. Those are little bubbles. But then we also graphed them on a regular rectangular coordinate plane system, so like XY plane. And that ended up giving birth to the idea of the vertical line test, where if you make a vertical line and if that vertical line intersects your graph more than once, then that means that graph is not a function. If it only intersects it once, and again, it's not just about one line, you have to make multiple lines. You try to see where your graph will, the vertical line will intersect your graph more than once. And if it doesn't, then it's a function. If it intersects it more than once, then it's not a function. But what I left off was talking about function notation. And that's what we're going to focus on today. Like, what can we do with functions? And don't forget, function notation, literally we're going to be looking at equations, but what we're doing is we're changing, instead of y equals x squared or y equals 2x plus b, y equals mx plus b, we're changing that y into, remember, this is f of x. That's what that means. That's what function notation is. But it works exactly the same way as an equation. All you're doing is changing the notation of it. So, for starters, the first thing we can do with functions, which what we did with equations, was evaluate. By evaluate, I mean we can plug in. Evaluating is just plugging in. So, for example, let's, given the function f of x, or, so something to note is that these functions, so it could either be f of x, it might be g of x, it might be h of x, and so on and so forth. The idea is that it has that, after the letter, it has the parentheses and then x inside that parentheses. So it doesn't always have to be exactly f of x. It could be g of x, and the function is 2x plus 1. And here, I'm going to bring this up here just because I want to write something, but this looks just like when we did y equals 2x plus 1. That's just the equation in slope-intercept form, if you guys remember when we were graphing those. But now instead of writing y equals 2x plus 1, we're writing g of x is equal to 2x plus 1. So that's the only thing that's changing, is the notation of y. X is still staying the same. But given this function, we can be asked to find the following, and this is what evaluation looks like. We can be asked to find g of -2. We can be asked to find g of, again, g of, or f of, h of, depending. We're actually substituting that x for an actual number. And we did the same thing before. We would, when we were graphing, so here, let me pull this up. So when we graph these here, that's essentially what we were doing. We were taking x and plugging it in to this equation. But instead of saying let x be -3 or x be -2, here what's inside is supposed to be x. So here we're saying x has to be -2. So it's exactly the same thing. Nothing's changing. So for the first one, to find g of -2, that means I have to look at this right hand side here. And I'm going to replace everywhere I see an x. I'm going to replace it with that -2. The same way we did it when we were graphing an equation using a table. We took your x and then we replaced it wherever we saw an x. -3 here, so I plug -3 in there. I want x to be -2, so I'm plugging -2 into that x. And then all I have to do is simplify from here. So that's going to be 2 times -2 is just -4 plus 1 leaves me with -3. And there's my solution. That's it. And what this is creating, if you wanted to graph this, it's also making an ordered pair. The ordered pair would be -2, -3. Because this g of -2 is still equal to y. So you always have to remember that in the back of your head. That function notation is y, just written slightly differently. Because we can define these equations a little bit further. So we give them more characteristics. And the characteristic we're giving this equation is that they are functions. So let's, hopefully you can pause the video, try the next two, and see what you get. But I'm going to continue. So here, I'm going to write g of, and then it's going to be 0. And everywhere I have that x, I'm going to replace it. So every time I always like putting parentheses around where the x was, and I've done that before. It's the same as we did it. Plugging in 0. 2 times 0 is just 0. And that's going to give me 1. And there's my answer. The next one, g of 1, same thing, 2 parentheses plus 1. That's where x used to be, and I'm plugging in a 1 into there. 2 times 1 is 2, plus 1 is going to give us 3. And that's it. There's not too much to the evaluation part. There are some evaluations that get a little trickier that we're going to look at. But this idea of evaluating, it's literally just plugging wherever you see your x, you're replacing it with whatever is inside those parentheses. Whatever it may be, you're going to just replace it. So here, let's say we're given another function. Here's another example. Let's say we're given, now we'll use f of x equal to 3x squared plus 2x. So there's a lot more going on here. So let's try to find, let's do f of -2. And it doesn't always have to be numbers. We can find f of... Alright, so I got cut off on the last video. So what I was saying was that when you're doing these functions, it does not always just going to be a number. It could be letters. Like for instance, f of a, f of x plus h. So, but the idea is just everywhere you see an x, you're going to replace it with one of these variables or numbers. So for instance, I did the first one, and what I always like to do, I always like to parentheses around everywhere there was an x. These parentheses are already there because of the notation. I put these parentheses in here because there used to be an x here. So to avoid making small mistakes, I like to take these parentheses and then plug them inside of here. So I took -2, there was an x here before. Plugged it in. The reason why it's important is because there's a big, like for instance, in this example here, sometimes when we don't put those parentheses, sometimes some students write this. But the problem is this, that square is only squaring the 4. It's only squaring the 2, which gives you 4, but then there's that negative comes and multiplies after. Where in this situation, it's squaring both the 2 and the negative. That's what ends up giving you a positive 4. So it's important to make sure that you're watching out for this. Again, and this takes care of that for you to not make this mistake. So watch out for that. But then once you plug it in, well, we know negative 2 squared gives me 4. 2 times negative 2 gives me negative 4. Now I'm just going to continue simplifying. 3 times 4 is 12. And 12 minus 4 is 8. And there's my answer for this one. Some people like to just box either this answer or rewrite it as f of negative 2 is equal to 8. Either one are perfectly good answers for me. But just so you're aware, some people sometimes just rewrite it all over again. Now, same thing as before. Everywhere there was an x, I replaced it with a parenthesis. This parenthesis is already there for the notation. But here, these x's that were here, I completely replaced them. And all we're doing is we're taking a and plugging it everywhere there used to be an x. There was an x here, here, and there. And I replaced it in every single spot. But there's not much to simplify because a when you square the a, it just gives you a squared. 2 times a is just 2a, and that's it. So all we did is replace all the variables with another variable, which is perfectly fine. We can do. But now this next one, that one might be a little trickier. So I'm going to do the same as before. But I'm going to make a little bit more room because I know I'm not just plugging in a single variable or a single number. I'm plugging these two terms in. So I'll make just a little bit extra room when I replace my parentheses here. So again, I'm making room. This is what I mean by I replace all my x's with parentheses. Because there used to be an x here, here, and there. And I replaced them because I'm going to plug in this x plus h inside of there. So let's do that. So I'm going to plug this in. And here, there's an x plus h. Here's going to go an x plus h. And here, I'm going to plug in an x plus h. Now, we're going to do this one to simplify this, not just there and stop. For this one, it seemed like that's all we did, just because you square an a just gives you a squared. But when you do x plus h squared, now that one you have to do a little bit more work. I'm going to do it here on the side. Because I know x plus h squared means x plus h times x plus h. And this, I have to use the distributive property. I have to distribute the first term to these two and the second term to both of these two. Which simplifies to x times x is x squared plus x times h gives you xh, and then h times x gives you another xh, and then h times h gives you h squared, which this simplifies to x squared plus, and then we can combine these two terms to give you 2xh plus h squared. Now I'm running out of room here. I wish I had a little bit more, but what's going to happen now is this gets replaced here, all of this, which then it will look like you're multiplying 3 to this whole thing here. It's going to be x squared plus 2xh plus h squared. And then don't forget, for this one, for this top one, all you have to do is distribute this 2 through. Then we're also going to have to distribute this one all the way through, which will become 3x squared plus 3 times 2 gives you 6xh plus 3h squared. This is simply going to become 2x plus 2h. Sorry, everything's crammed in there. I just ran out of room, but let me get a sheet of paper to finish this off. So I'm going to put this here like this so I can continue. Hopefully everyone can see. So what ended up this becoming, so f of x plus h is equal to, remember I had to distribute this out, so I figured out what x plus h squared was. And then I distributed the 3 to each one, which left us with 3x squared plus 6xh plus 3h squared. And then we have to just input this part, which is going to be plus 2x plus 2h. You're asking, why do we even want to do this? Because for those of you who are going to continue taking more math courses, in calculus, this is going to be a big part of the idea of limits and finding derivatives and finding slopes of tangent lines and all this extra fun stuff. You'd have to know how to evaluate a function this way. Plugging in x plus h or plugging in different letters and numbers to help you simplify your function. We're eventually going to look at something called the difference quotient. That's going to involve doing all this evaluation and simplifying, but that's how we would plug that in. Those are different types of evaluation that you can see. Sometimes they like to ask you to evaluate, but they do it more, I would say, implicitly. For example, they can ask you to find the x and y intercepts of a function. Remember, we talked about x and y intercepts when we were graphing linear equations. And x and y intercepts exist for any type of equation and any type of function. All an x and y intercept is just the point where your graph crosses the x-axis. So if we're looking at, for example, here, well, we can see here at this point, it's crossing both the x, it's touching the x, and it's crossing the y-axis. So here is both an x and a y-intercept, and that's the origin. And the whole point is, for example, let's say we're looking at this one. Well, this one is intersecting the graph in two places. That would be the y-intercept, and this would be your x-intercept. And you can do that for any function. But remember, you have to remember what we said about all x-intercepts. All x-intercepts had this in common, that they all had some number for x, but 0 on the y, because that's the only way that it can actually have an ordered pair can be on the x-axis, because you're not shifting it up or down at all. You might move left to right on the number line, but you're not going to move up or down at all. So now for the y-intercept, we said that they all had a 0 for the x and some number for the y, because that meant it didn't go left or right at all on the graph. It just went up or down to stay on the x-axis, on the y-axis. But we can transfer this idea to looking at functions, because to find the intercepts of a function, we have to just rewrite this, because we're saying that we're telling you that y has to be 0 in this situation, and here we're saying that x has to be 0 in this situation. And remember, with function notation, y in this situation now is f of x. So what we're going to say is that to find your x-intercept, you're going to have to let f of x equals 0. But what you're saying is you're saying that y can be 0, because f of x is y when we start talking about function notation. And for the y-intercept, we have to let x be 0. So that means we have to find f of 0. Here, you have to let f of x equal 0. So this one's the y is equal to 0. In this case, your x is being equal to 0. And whatever this gives you on this side, that's the number here. Whatever you get on this side, that's the number there. So here you find the x. Here you're finding your y. Because remember, this f of 0 is your y. But this f of x is your y. But that inside of it, that x is just your x. So let's do an example of that. Let's actually try to find our intercepts with the given function of... Let's look at an example. Let's look at f of x equal to x squared minus 4. And don't forget, the x-intercepts are not just numbers. They are points. So you have to be able to write those points. One that's not too bad to find is the y-intercept. So for starters, if we find the y-intercept, that means that we're going to have to find f of 0. So I do f of, and then that means I'm going to evaluate. What have we just been doing? We've been evaluating these functions. So everywhere I see an x, I'm going to replace it with 0. So 0 here, 0 goes here. But I know 0 squared is just going to be 0. And this is just going to be equal to -4. Now I have my y-intercept. My y-intercept is, again, my x is 0. But then whatever I get in the outcome, this represents my y. So it's -4. That's going to become important once we start looking at quadratics a little bit further. But for now, that's how you would find a y-intercept. Now for an x-intercept, this we have to let our f of x equal 0. So when I'm looking at this part here, this f of x equals x squared minus 4, what we're doing is I'm going to replace this f of x with 0. And then it's equal to x squared minus 4. And now, again, you're trying to solve for that x to find that x-intercept. So that's why here you're solving for x. Now, hopefully, you can try to think of what type of equation is this. And remember I said, as soon as you see an equation that has a power greater than 1, you quickly resort to the zero factor property, which says that you move everything over to one side, you set it equal to 0, try to factor the opposite side, and then set each factor equal to 0, so on and so forth. But sometimes you can't factor everything. If you could, that's great. If you can't, then maybe you have to use your quadratic formula. Or in this particular example, since all we have is the x squared and the constant, we don't have that middle term of x, then you can either just move this 4 to the opposite side and then use the square root property. Or you can factor this knowing that this is the difference of squares. which is x plus 2 and x minus 2. And then you would set each factor equal to 0. You'd have x plus 2 is equal to 0, or x minus 2 is equal to 0. Where here, this x gives you negative 2, and this x will give you positive 2. Which you could have done the same thing by moving over that 4. So if I added 4 to both sides, that will give me x squared is equal to 4. And I could have used the square root property, which simplifies the square, but don't forget you have to add the plus or minus, and the square root of 4 is 2. And there you have the negative and positive 2. Either way works perfectly fine. But again, I wouldn't just say, let me box these answers, I'm done. When we were just solving quadratic equations, yes, you were done. That's all you had to do. But here, the question was about finding the x and y intercepts. So I had 2 different values of x. So that means I'm going to have 2 different x intercepts. And I'm going to have one here. So again, my y is, my x, one of my x's is negative 2. And I know my y was 0 because I let it be 0. And then my second one is x is 2. And then my y is 0. And these are my 2 x intercepts. So again, it's just changing up the notation a bit on how to find these. But you're still either plugging in 0 for the the function notation side, or you're just plugging 0 into your x. And again, you just have to get used to seeing it slightly different, but it still means the exact same thing. You just want to be careful when you're looking at it. And the idea of why we have 2 and there's only 1. Again, I'm not going to graph this one, but again, like I said, you have to be able to recognize what type of function this is going to be. So let me show you really quick which function this is. Remember I said, whenever you see that x squared anywhere, again, I know there's more numbers attached to it and so on and so forth, but this is the key thing to look for, because once you see that square, you automatically know that this is going to be some type of parabola. Again, I don't know the exact graph of this, but I'm just going to take a guess that it does something like this. And the reason why I say that is because I know I had 2 x-intercepts. So that means I have to cross the x-axis twice. And that's the only way I'll be able to cross the x-axis twice. That if it curves upward and this point down here is below the x-axis. Because if it looked like this situation here, it never actually crosses the x-axis. Or if you did this, let's say if a parabola pointing down, that doesn't cross the x-axis either. So in both of these situations here, there would be no x-intercepts. The only time you'll get an x-intercept is if it somehow is below, or if it's pointing downward, it has to be above the x-axis. The only time it will actually cross the x-axis. But in every single situation, we always had a y-intercept. And I know this y-intercept at 0, comma. Because then, for example, if I was trying to graph these x-intercepts, here's 1, 2, 2, comma 0. That's this one right here. I can go 1, 2. And that's this one right here. But then I know my y-intercept has 0, comma negative 4. So that's 1, 2, 3, 4. And that's 0, comma negative 4. This is 2, comma 0. And this one is negative 2, comma 0. So, again, I know it's a parabola. And I know where these x and y intercepts are. I have a rough idea of what this graph would look like. And if you actually graphed it on a graphing calculator or you use Desmos to graph it, you would see that the graph looks roughly like this. So this is just so you have an understanding of what how all this connects. Why we looked at these graphs, knowing what they're supposed to look like, and so on and so forth. But now, something else that we looked about on the previous video in functions was, I've left it out, his domain and range. We're going to focus on his domain for now. And remember, the domain is the set of all x coordinates. So that's what the domain is. That's the one we're going to focus on right now. The domain is a set of all x coordinates. And we're going to try to see if we can find the domain. For example, we can do it for, we can already do an example. We can say find the domain. And the first example could be f of x equals x squared minus 4. So when we first did the domain, and when we started 2.3, we looked at the relation. We looked at all the x coordinates, and it was 2, 3, 1, and -1. But here I'm only looking at 4 relations. But again, I already know that this is some type of parabola that has an infinite amount of ordered pairs. So the relation of this, we'll be looking at so many ordered pairs. I can't list out this. I can't list out this 0, this -2, this 2, and every other single x coordinate on this graph. There's too many. I can't write these by hand. So when we start looking at functions and their domain, or the domain of an equation, the idea is we want to know all the x coordinates that satisfy this function. And sometimes, to help us do that, we want to think about all the coordinates that won't satisfy this function. And what I mean by that is there any value of x that you can think of that might make this undefined? Something that's not possible to do. For example, can you plug a negative inside of this x? Well, we did something like that earlier. Where is it? We plugged in a similar. Here was an x squared. We plugged a -2 in, and that was perfectly fine. I could plug a -2 in here. That's going to be perfectly fine. I can plug in zeros. I can plug in a fraction. Again, even though it's going to look ugly, I can still plug it in. The idea is you want to see, is there any x value? So now you have to look at the entire x-axis. It's like a number line. You have 0 in the center, positives on the right, negatives on the left, and a bunch of decimals in between. And they go on forever. Anywhere in here, so let's say if we're looking at just the number line, right? Because we're not worried so much about the y-axis right now, because we're only worried about x coordinates. So I'm worried about the x-axis, where here's 0, 1, 2, 3, so on, -1, -2, and goes on forever. And then there's a bunch of other numbers in between as well. You want to ask yourself, do any of these numbers make it impossible to do inside of here? Again, you can plug in a decimal. You can do 0.2 squared or 0.5 squared. It's going to be an ugly number, but then that doesn't mean it's not going to be a real one. So if you plug in negatives, -1 squared is 1. We already saw that if you square -2, That's just going to give me 4. So that would be fine. And the idea is there isn't anything that doesn't work. Every single number on this x-axis will work perfectly fine on this function. And the idea comes from looking at this graph. Because if there was something that was not possible, that means your graph would have some type of gap or hole inside of it. But if we see these, remember, these have a course. This ordered pair here has some corresponding x. This ordered pair has an x to it. This ordered pair has an x to it. And all these have some x. All these ordered pairs have some corresponding x to them. And this opens up gradually forever in this direction, and this opens up gradually to left forever. Meaning that there's going to be an x coordinate everywhere. There's no gap here. There's no hole on this graph. It goes up. It goes on forever with no issues at all. So that means that there's 2 ways to write your domain. You can use interval notation, which would be, you can use anything all the way to the left, anything all to the way to the right, and that would be negative infinity to positive infinity. And everything else in between. Because it's saying that entire number line is possible. We can also use set notation. Set notation is a little trickier, but becomes really nice for certain examples. Remember, if you're using set notation, we have to pull out the braces. And the way set notation works is that you have to, I know we've been plugging in ordered pairs in here, but you're not going to write down every single ordered pair that's possible. You would be here forever, literally forever, and you will never finish. So the way it works is that you have to write the variable that you're writing the notation for. So we're writing the domain for x. If you're doing range, then you would use a y. Now, you have to, this vertical line means such that. And what you're saying is that I'm going to tell you about the x variable. And this is saying after here, I'm going to tell you something about this variable. And that thing is, so that thing is that x is, meaning I'm telling you all the x values that satisfy this function. And we use this symbol here. And this symbol means all real numbers. So that's implying every single number that's on that line, on that x-axis. That's what that means. That every single number works perfectly fine. Now, there's other functions that are slightly different. So, for example, we could look at, let me pull it up right here. So B, we can look at g of x equal to the square root of x. Now, we have to sort of build off information that we learned from before. And what I mean by that is, what do we remember about square roots? Sit and think about what did we say about square roots when we were doing these. In terms of real numbers. What problems did we usually have when we dealt with square roots? Even though we figured out the solution to that problem, what was our original problem when we were doing these square roots? And hopefully you're telling yourself that it was negatives. Negatives were the problems that we had. Because every time I plugged the negative inside of here, I ended up getting some imaginary number. That's when we solved that problem by using complex numbers to solve the problem about negatives. But if I'm just working with the x-axis, there is no imaginary numbers on this axis. So I only want all the real numbers that satisfy this function. So I automatically know, remember, it's not that x cannot be negative, is that anything inside the radicand, so that's under the radical symbol, cannot be negative for square roots. So you want to start asking yourself, what is the very first number that's not negative that you are allowed to use? Let's say if we're looking at a number line. What's the very first number that's not negative that we're going to be allowed to use for this function? And if we look back at when we actually graph the square root of x, the graph starts giving us an idea of what the function, the domain is. Because if you notice, the graph doesn't actually exist on this entire left-hand side. And the reason is because we can't have negative numbers. Because those, even though we've solved the problem and we get a complex number, this x-axis does have no complex numbers on it. It's only all real numbers. And remember, when we graphed, the very first number we were able to use is have 0. And then we're able to use 1. And you're able to use 2. It's ugly. You're also able to use 1.5. But you would have to try to find what the square root of 1.5 is. And to do that by hand is difficult. But here, again, the fact that this is a solid line, there are x coordinates at every single point on this graph on this side. There's a bunch of corresponding x's. So every single value is perfectly fine as long as it's not negative. So when I start writing the domain, that means that the very first number I'm allowed to use, and it's included, so remember, included means brackets, is 0. But then every single number to the right. So again, least to greatest. Those are all the values of x that are perfectly fine. But now in set notation, same thing. We're saying x. We're going to talk about x and such that x has to be... What does x have to be? Again, I wouldn't say in words x has to be 0 or bigger than 0. You can start thinking about how can we write that x has to be 0 and it can also be bigger than 0. Instead of using all those words, do we have a mathematical symbol that tells us we can do this? And hopefully you remember that we can say x can be equal to 0, or it can also be greater than 0, meaning bigger than 0, and it could be equal to 0. Again, I wouldn't use all real numbers, or some people use, but that sort of satisfies what x is. X can be any number that's greater than or equal to 0. But even with this example, you want to be careful, because sometimes you end up having an example like this. G of x is equal to the square root of x plus 4. And then if all you're thinking is, oh yeah, x can't be negative. But if I did, let's say, g of negative 3. Remember, if I'm replacing that x with negative 3, that means I'm going to replace this x with negative 3. And I always use parentheses to replace them. Well, negative 3 plus 4 just gives me the square root of 1, which is equal to positive 1. And this is a real number. How was I able to use a negative number and I was able to get a real number as an answer? I thought we said that we're not allowed to use negative numbers. And the idea is not that x cannot be a negative number, is the radicand cannot be a negative number. The radicand, the smallest the radicand can be is 0. So that means you want to start asking yourself, where is this radicand equal to 0? And if you look at x plus 4, you should start thinking, wait, I get 0 if x is negative 4. So that means that this radicand starts where x is negative 4. So that means the radicand is somewhere over here. This function looks probably like this. It starts right here at negative 4 and then probably continues in that direction. So when you're writing the domain of this function in interval notation, again, I saw negative 4 works, negative 3 works. That means negative 2 should be fine. 1, 0. Because I plug in 0 here, I'll have 4. The square root of 4 is 2. That works perfectly fine. And you can see that here. Because if I plugged in 0, so if I did g of 0, that would be the square root of 0 plus 4, which is the square root of 4, which is 2. And this gives me an ordered pair of 0, 2. And look at that. That's actually a y-intercept. Look, it's right there exactly where I drew it. So that graph is right here. So that means this starts at negative 4 and then continues on forever. Remember, negative 4 is included and we never include infinity. Parentheses always around infinity. So it's not that the x cannot be negative. It's that the radicand, everything under here, has to be either equal to 0 or strictly greater than 0. So that means that in this situation, in set notation, we know that x has to be strictly greater than negative 4, but it could also be equal to negative 4. And I like to explain it that way to begin with, because the idea is that whatever's, so I'm going to put a note here. A note is that for here, the radicand has to be greater than or equal to 0. The reason why that's important is what I could have done is that, well, I know the radicand here is x plus 4. And I'm saying the radicand has to be strictly greater than or equal to 0. And wait, didn't we spend so much time looking at inequalities? Yes. I know how to solve this inequality. I just subtract by 4. As long as I'm not dividing or multiplying by negative, I don't have to worry about this inequality. It's going to be x is greater than or equal to negative 4, which is, that's what this says, and that's exactly what this is saying. So, again, sometimes it's useful to think about what doesn't work, because when you're doing the domain, you're being asked to determine what does work, what actually satisfies the function. And this starts making you think about what functions do we have restrictions. So if we look at all of these functions, you want to start asking yourself, did we have a restriction? Does something make this undefined? Does something make x cubed undefined? Does something make square root undefined? And we just did that. And that was negative numbers under the radicand. Is there anything that makes the absolute value undefined inside, not outside? Does anything make it undefined inside? And then there's actually a function that I didn't write here, but there's also this function of 1 over x, meaning a fraction. Are there any restrictions when it comes to fractions? And there is. Remember, your denominator cannot be 0. So if we're looking at an example like this, let's say if I want to find the domain of this function, well, I know that every number works. I know everything's perfectly fine. I know the only problem that we've been told is that the denominator cannot be 0. So if I'm writing my domain in interval notation, that means if I'm looking at a number line, That's the only one I don't want to use. Everything on the left is fine. Everything on the right is fine. But that ends up making two different intervals. One that starts from negative infinity and stops at 0. And there's another one that starts at 0 and goes on to infinity. And remember, there's always parentheses around infinities. And since this 0 is not included, I put parentheses around these zeros. And remember, we have to use the union then. And that would be our answer. Where this is where set notation becomes a little bit nicer. Because for set notation, all I have to say is that instead of writing, for example, if you're telling your friends that I work... So let's say if you worked Monday, Tuesday, Wednesday, Thursday, Saturday, and Sunday. If your friends asked you when you worked, you wouldn't say it that way. You wouldn't say I work Monday, Tuesday, Wednesday, Thursday, Saturday, and Sunday. Or maybe you would, I don't know. But normally you would say, oh, I work every day but Friday. That's much quicker than say, oh, I work Monday, Tuesday, Wednesday, Thursday, Saturday, and Sunday. I work every day but Friday. And that's what using this set notation does for us. Because the example that we did here, oops, let me move this. This, every single number works. So instead of writing 1 works, 2, 3, 4, a half, a third, 1/5, 2, 5/17, we just said all real numbers. But for this one, instead of writing everything out or like doing all this extra work, I can still say X is all real numbers except 0. So I'm saying X, telling you X, I can use every single number except 0. That's like saying I work every single day but Friday. That's sort of what this set notation helps us do. Instead of trying to show everything, these interval and then this second interval, and there's a union between them, all of them but 0 works perfectly fine. But the same thing as with the radical. Don't get stuck on, well, that means that X can never be 0. No, because there's examples that are, I'm going to do it right here, even though I'm just scratch paper. There's examples like this. There's examples that are 1 over X minus 3. Here in this situation, I plug in 0, and that just gives me, let's say I have a G of 0. That's 1 over 0 minus 3. That just gives me negative 1/3. Which that's a real number that's on this side of the graph somewhere. That's perfectly fine. So you want to start thinking which, it's not that the X cannot be 0. It's that the denominator cannot be equal to 0. The denominator. If I'm looking at my denominator here, it's X minus 3. So I need to think what value of X would make this X minus 3 0. And hopefully you're telling yourself, oh, it's 3. If I plug in positive 3, 3 plus 3 gives me 0. So that means when I write my domain, it'd be X such that, like I said, you can say it's all real numbers, but 3. That's the only number that makes it undefined. Or if you did interval notation, again, it would make 3 intervals. So there would be from 3 would not be included, everything to the right and everything to the left. So I'll be negative infinity, stop at 3, start at 3, and then to infinity. And parentheses around both because none of them are included. So that would be the example for that one. And sometimes they like to do other examples that try to trick you. Because let's see, for instance, let me now grab another sheet of paper. Here, got a new sheet of paper. They can ask you to do, let me switch it up. Let me do h of x. They can ask you to find the domain of this, x squared plus 4. Now it's getting a little trickier. Because you want to start thinking, well, if you're looking at the last example, you could be saying, oh, I can just use -2. Say I do h of -2. I know that's going to give me 0. Because -4 plus 4 gives me 0. But remember, if we're plugging in, again, replace the parentheses with the x with the parentheses. And remember, when that negative is inside the parentheses like that, it actually becomes +4 plus 4, which gives me 1/8. Well, that's not 0. Okay, then 2 must work. But 2 squared is going to give you 4 plus 4, which is also 8. And if you plug in 0 here, well, 0 squared is 0 plus 4. It still gives you 4. So that's not 0 either. In this example, there is no value of x that makes your denominator 0. It's impossible. So that means the interval notation is just, that means every single number works. The set notation is x is all real numbers. So you just want to make sure you're being thoughtful of when you're doing these examples. Don't just go straight, resort to giving a random answer. You want to be a little thoughtful and think about what it's asking for. And remember, the only two that have restrictions are the square roots and the fractions. All of these other ones have no restrictions to them whatsoever. This has no restriction. This has no restriction. No restriction. And no restriction. So these will always have the domain of all real numbers, or -infinity to infinity. And you can see that. They go on forever, no gaps. They go on forever, no gaps. This goes on forever with no gaps. This one, you can see how it doesn't exist in certain places. And this one, again, it's just like the parabola. Goes in every direction forever without any gaps. So, just be thoughtful before you start just writing, oh yeah, x can be 0, or for square roots, oh, it can be negative. It can be, depending on what's inside the radicand. And x can be 0 for a fraction, depending on what's on the denominator. And sometimes they're a little more difficult. Sometimes you do have examples that are like f of x is 1 over x squared 5x plus 6. Now these, it's a little bit trickier to be like, well, what value of x when I square it? And then I add 5 times that number plus 6 is going to give me 0. These are a little more difficult to do. This example, you could think about it in your head. I know 3 minus 3 gives me 0. Even if it was one that said like 1 over x plus 2, well, I know -2 plus 2 gives me 0. This one involved a little more thought. But remember, the main idea is that the denominator cannot be 0. I do not want this to be equal to 0. So let me see where it is equal to 0. I want to know where x squared plus 5x plus 6 is equal to 0. Because when I know it is equal to 0, I know to exclude those numbers. And now, look at what we have here. This is a quadratic equation that, again, we have a power greater than 1. It's already equal to 0. Remember, the first thing you should do is try to factor. But when you're factoring, remember, the first thing is always, is there a GCF? No. Is there 4 terms? No. Is it 3 terms? Yes. So I use this method, just like how we did before. Here goes my 6. Here goes my 5. 2 and 3 is going to work. So that's x squared plus 2x plus 3x plus 6. I group the first 2. I group the second 2. I always grab the sign, but I put a plus to remind me they're not multiplying. GCF here is x. I have x plus 2. GCF here is 3, positive 3. That leaves me with x plus 2. GCF between these two is x plus 2. And I'm left with x plus 3 equal to 0. And then I set each one equal to 0. So remember I said factoring was going to be a very useful tool when we did problems later on. You have to be able to do this quick. You can't just take your time. You have to be able to see this and know it's 0. Try to factor quickly. Find those. These are the two values at where this denominator is 0. Don't be like, oh yeah, these two are my answers. No, these two are the ones that you do not want to use. So that means when it comes to your set notation, this is where set notation gets even nicer, because all I have to do is remember every day but Friday. So I can use every single number, just not -2 or -3. Where if I did interval notation, this is where interval notation gets a little more difficult. So if I make this number line, I know I can't use -2 and I can't use -3. But I can use everything in between them and everything to the left and right of them. So that means I'm doing 1, 2, 3 different intervals. One that's from -infinity to -2. Remember, it's not included. And then from -2 to -3, both are not included. And then from -3 to infinity, and they're both not included. So let me block that off. And then union, or let me write that again. So -infinity to -2, -2 to -3, and then -3 to infinity. And then union at all these places. So that's where the set notation becomes nicer. But if you like the interval notation, that's fine with me too. But again, try to think about these and see what do you think. It's about the denominator cannot be 0. Don't always resort to just making this equation. Think about it first. Think about what can give you 0 before you resort to doing this. Same thing with the square root. Don't just jump to creating that inequality of greater than or equal to 0. Sometimes you could just think about what's the smallest radical you can get just by looking at it. Sometimes it's not so straightforward, but you can try to do it. Alright, I'm going to end this here. Let me give you some homework for you guys can do, and that should be it. Alright, here's the homework. Sorry that there's homework from the last video too. So I think these problems here are from we did today. These are from before. But identifying if a graph is a function. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay. It's a lot of homework problems. More than I'm used to giving. So let me take this one off. Let me take that one off. I'll take off 30, another one. That's a lot of problems. I don't want you to be there forever. Let me take out. These shouldn't be too bad. I'll take out 44 also. So try these. I know I didn't take off too many, but 15, 17, 20, 23, 25, 26, 35, 38, 45, 51, 55, 56, 57, 97, 99, 100, 103, 75, 78, 81. Again, this stuff is important, so try to work on these. I know it's a lot. I try to do a few a day, maybe jump around doing some of them. Because these three are roughly the same. A lot of these are finding the domain. So just do a couple of them. But see if you can finish them. If you have any questions, please let me know. Other than that, have a good day.